All right, so my name is Maia Tarnas. I'm a PhD student at UC Irvine. And I've had the really great pleasure of working with Ryan and Elena for several years now. And a lot of our work has been with time series. So this is a really exciting opportunity to get to share that with you all. So to do some brief intros, Ryan Simpson, he's a second year PhD candidate at the Friedman School. His degree is in nutrition epidemiology and data science under Elena's guidance. And a lot of his work focuses on infectious disease time series modeling and applications for real-time outbreak surveillance and forecasting, specifically for enteric and respiratory illnesses. So some recent work has been on techniques to assess publicly recorded surveillance data, including some work on modeling seasonal outbreak features, including those in Yemen and cholera, and with SARS-CoV-2 in Middlesex County, Massachusetts. And then Dr. Elena Naumova is the professor and chair of the Nutrition Epidemiology and Data Science Division at the Friedman School. Her research interests are vast, but to capture a couple of them are the impacts of natural disasters, climate change, extreme weather on health and nutrition of public and vulnerable populations. She is an elected member of the International Statistical Institute. She served on a number of scientific panels and is also the editor-in-chief of the Journal of Public Health Policy and on the advisory board of the International Journal for Environmental Health, Environmental Research and Public Health. So two really great and knowledgeable speakers for you all today. And we're excited to get started. So with that, Ryan, I will turn it over to you.
Thank you, Maya, and thank you all for being here. I'm so excited to kind of talk about a topic that I know is near and dear to my heart and Elena's as well, of time series. It's pretty much going to be more of a kind of not a formal discussion, but more of an informal chat, talking through some of the methods and applications of time series. Feel free to throw your questions in the chat or raise your hand, and as they come, we can kind of walk through it. But today we're going to really focus predominantly on kind of describing the components of time series. What are their properties? Describing different types of common trends or perhaps irregular trends that you might see. And more importantly, the concept of seasonality, which is something that we've done a lot of research on recently. And then also discussing important aspects regards to data and the roles in which data quality, data credibility can play when we start to think about how to model time series data, and then maybe propose at the end a few metrics to think about to expand beyond the types of data quality and credibility metrics you see in standard epi or nutrition epi literature, and think about more of how they apply to time series properties and components. So just to kind of get the ball rolling, what are time series, right? So when we think about time series, they involve what we might consider as three different components. We have the data, the distribution, and the types of methodological analyses that you would use to assess these data. So the time series data, it's a set or a sample of time reference observations that have a specific identified period, cycle, or unit, versus the distribution, which you can think about in the context of how often does a certain thing happen in a certain period of time. So we're usually thinking about this more on the population level. We're thinking about the counts or frequency in which a specific event occurs within a day, within a week, within an hour, within a year, as kind of depending on the type of data you have. And then the time series analyses, which is more so getting into the modeling standpoint, is going to discuss more of the types of trends, the types of patterns we see, the types of methods we use to analyze those types of patterns. And we're going to discuss a variety of different ones today, lots of examples, and feel free to stop along the way. So just as kind of a classical example of what a time series might look like, you can see that on the horizontal axis here, we have time in months. We have this wonderful color coding that represents each of the different years as we go. And so when we're thinking about what the data are, we're talking about time reference observation. So similar to how you might have a scatter plot with the relationship between X and Y in a standard regression model, now we're thinking about still the relationship between X and Y, but in this case, X is time points. And those time points have a specific frequency, as we said, month. We can see that they have different cycles, which we've defined as years. And we can then think about what is the type of distribution that we have, which not like the types of distributions, or I guess similar to the types of distributions you'd see with the histogram of the number of frequencies of a specific observation level. Now we're saying the exact same idea, but what we're thinking about is the frequency of months in this case, in which the level of the outcome hits that specific value. And so one of the common attributes of time series that you see in that rotated histogram on the y-axis is you see that oftentimes when it comes to disease outbreaks, we end up having a lot more frequency of time units where there are perhaps fewer counts or fewer cases or lower rates as compared to kind of the stretch of the distribution, which may go quite higher when we're starting to think about outbreak type of events, which is particularly of interest when we start thinking about how you model infectious disease outbreaks, foodborne outbreaks, et cetera. And with that regards, you can hopefully see that blue line. I know blue on blue might be tough, but if you can see that curved blue line, we're also thinking about the types of analyses where now we're thinking of y as a function of t. So the outcome as a function of time, and then that function of time can have a variety of different ways of modeling it based off of whether we're thinking about time in what construct, what types of trends we're considering. And all of that depends on how we set up our model. So one of the basic, again, describing a basic pattern, it's just thinking about this basic linear increase or a linear decrease. And so as we can see, we have our standard function, y is a function of time, beta naught plus beta 1t. And we can say that our time period or our study period begins at this kind of t naught going until tn. And so our study period is now the number of time units that are occurring between the beginning of our period and the end of our period, right? So thinking about the data points, thinking about observations here, what we're really talking about is how many time points do we have, not necessarily the number of observations at each time point, right? That is where we're kind of thinking more from the outcome standpoint. So if we're thinking about a general linear increase, we're saying that now in this equation, beta naught or beta 1 is greater than 0. And so in that case, we're seeing this linear increase over time of a general rise in the outcome. To that same extent, we can then think about variability around that. So if we have a linear increase, which you see from the dotted line, we can think that that may now increase at an increasing rate or increase at a decreasing rate, depending on what we may have in terms of additional nonlinear components of our time series model. So in this case, we may have the linear component of trend, and then we may have time squared, time cubed, time to the fourth, which are all going to provide different constructs of how it may accelerate over time or decelerate over time, depending on the increase or the decrease that's related with that beta 2 coefficient.
Ryan, can you comment on whether it matters if the duration between the time points is varied?
That's a great question. So when we start thinking about time series, usually one of the properties we want is there to be frequent and consistent reporting over time. So a time series, and you can think about it in the same stance that we may do for sample size, for example. In a standard regression model, usually you want at least 30 observations, but ideally more is better. Similarly, with a time series, you want more time units in order to have greater effect size and greater power in any of the time series analyses you're doing. So if you were to have one observation, say at 1 month, and you don't have another observation for another 100 months or another 2, 3, 10 years, whatever it might be, you may not be able to very easily see patterns between each of your time points. So the frequency matters, the number of observations matter, and the consistency matters. And that's something we'll talk about a little bit towards the end. When we start talking about data credibility, we think about how complete is the records that we have, how often are they being reported, what's their availability and the velocity of their reporting. If we only have yearly data, we need a lot of years in order to really understand trends. If we have a lot of, say, daily data, we actually have quite a bit of data points just for 1 year. But then the question becomes which pattern you're trying to analyze, right? Thank you for that question. So we can think about this kind of array of different possibilities. Now we have, again, our increasing trends, we have increasing and decreasing rates, and it all comes down to the way in which we construct the model to think about the different types of trends that we have. And we can get far more complicated with cubic terms and to the fourth terms. We can also use different types of functions. It doesn't just have to be these linear or polynomimetric terms. We can think about, say, functions, things like harmonic functions, which we'll talk about a little bit later, that are able to pick up other types of curvatures, maybe similar to the types of curvatures you see here, that aren't just a simple increase or decrease, but instead have more of an oscillating pattern. And similarly, when we have a decline, what we're really saying is that, again, the same structure in terms of changes over time, but now we're saying that over time from the start to the end, we're saying that the overall decrease in the outcome as we go. And in this case, we can say that at the value that we have of the outcome at the ending time point is now less than the outcome that we have at the beginning. And similarly, we can think about that with acceleration. So as compared to what we had before, where we're seeing acceleration, it's increasing at an increasing rate. We can now say that it's decreasing at a decreasing rate, or alternatively, decreasing at a decreasing rate. So decreasing rate, we're thinking about coming a little bit more towards a perpendicular line, or a horizontal line, I should say, and as compared to something that may be at an increasing rate, which appears to be pushing more towards a vertical trajectory. And again, different arrays of doing that. And we could also think you may have, as you introduce things like a third degree polynomial, you may have one trend that's increasing, one that's decreasing, so that it has, again, some of that oscillation. More often than not, when you're playing with less nice, pretty, comfortable, wonderful, clean data, you may end up having different trajectories that look a little bit like this, where you start having these irregular patterns and needing to explain how these patterns come to fruition and what exactly is their driver. So in this case, we could say, take this example of instantaneous shifts down. What we're having is a specific pattern that we see that maybe it's oscillating, maybe it's a straight line, but we see a specific plateau effect. We see a critical point, and at that critical point, we see this instantaneous shift from one level to another level. And one of the ways that we can introduce this concept within time series models is to not just have our trend term, which is what's dictating kind of these, well, actually the absence of a trend term in this case. We can say that we have one value here and one value here. But now with this beta 2 term, what we're introducing is 2 time periods. We're introducing kind of before the critical point and after that critical point. And we're saying that the difference between these 2 time periods is that instantaneous shift, which we've defined as B2, where beta 2 is being less than 0, meaning that we're shifting down, or if it was greater than 0, we would be shifting up. And you might say, well, when might we see this? Because this seems, too gross and crazy to be true. This would never happen in real data. And it actually does. It happens all the time. So one example that we have here is current work going on with Emily Sanchez. It's on food recalls using the US National Outbreak Reporting System. And actually, this comes not from anything to do necessarily with patterns in the data in the sense that the outcome is changing dramatically, but also this idea of the changing in reporting of surveillance systems. So under the old surveillance system, there was no information being collected on food recalls, which you can see that the outcome here on the y-axis is the number of outbreaks missing information on food recalls, which is that orange period. And we can see that as soon as we change over to a new surveillance system, and that new surveillance system includes a question that now asks, was this outbreak a recall? We can see that we immediately drop with that instantaneous shift now to no longer having missing information. So we go from having all of this missing information to now very clearly knowing, was an outbreak a recall or not a recall? And that manifestation is something that happens outside, artificially perhaps, of what you could think about actually being a pattern of the disease itself or of the outbreak itself. This is just something that's a byproduct of the surveillance system that now, once we're able to pick up on that, we see a completely different pattern that we otherwise saw before. Similarly, one irregular pattern you might see is an increasing trend or a decreasing trend, but now we're seeing instantaneous shifts up or down with a trend instead of seeing something that may have been a flat curve as before. So in this case, we still have our critical time point and we still have our period before and after, but rather than having beta 1 before, if we go back to our previous example where we have no change over time, and instead we just have this instantaneous shift. now we're moving to where we do have the same trend over time for both time periods, and this instantaneous shift down to kind of reset and then expand on an upward trend. And so where we might see this is when we start thinking about, in our example with our research, is in Yemen as we focus on food consumption and food strategies. So one of the outcomes that we've been looking at in detail is poor food consumption. And so this is the percentage of households that have poor food consumption over time. And what we see is that it almost moves, I won't say it's cyclical, but it almost moves in this kind of consistent pattern where we see a slight increase or a slight growth in terms of the numbers that have poor food consumption, and then this instantaneous drop, and we start to kind of grow again. And we actually started looking into this, and some of the work by Dr. Anastasia Marshak also dives into this when we start talking about the seasonal patterns of malnutrition. We see that there are coping strategies that over time, individuals in different areas, specifically subsistence farmers, may have in order to increase over time or decrease over time their storage of different food crops. And so you actually see that their consumption patterns will worsen until they get to that next harvest period, for which they now have new stores of grains or of other products, in which case now we're beginning the season again, where we start to end up having poorer food security. What you also see is that there's some gaps that come in the data, and it just so happens this time period overlaps with the Yemeni civil war, which is actually the context of our most recent publications. And one of the things to think about is reliability of the data, which again, we'll dive into a little bit later, but you may see some of these instantaneous shifts. We assume that it maybe is the depletion of foods between harvests and lean seasons, but it may also be that we just simply have an absence of reporting, or we have an absence of information due to issues in being able to collect information in certain areas that may be experiencing war. And another irregular pattern that we might see is this kind of almost an inverse to the extent where we have the increase over a certain period of time. We then have a plateauing effect, to which we then have another increase. And that increase may be of perhaps a different trajectory or a different trend than what we see in the previous period. So in this case, we have what one might define as a segmented time series approach, where we have different critical periods that will present themselves as we see with Z1, Z2, and Z3. And we're able to map out what their trajectories would be as a beta 1 increasing with a specific trend, beta 3 increasing with a slightly different trend, and beta 2 having no trend in between, where it's just simply plateauing. And so what we would see in this case is our recent works when we're talking about SARS-CoV-2 tests in Middlesex County, Massachusetts, as we go through different periods of policy interventions that are being put in place. And so what you can see here on the y-axis, we have tests per million persons, and here we have different days. And so you can see there's actually this day of the week effect, which was really the primary goal and objective of analysis for our manuscript. What we can also see is as we go from the more stringent phases, which are this kind of darker red color, to the less stringent phases, which is where we start to see this lighter yellow and green, obviously green being before the pandemic hit, we're starting to see that tests all of a sudden increase very dramatically or during a more stringent period. As we go to a less stringent period, they somewhat plateau. Then we go into another less stringent period, specifically around maybe some of the start to school again. As we come towards August, we see the increase again. Or in reverse, we see declines as we come closer to after the big holiday season around Christmas and the New Year's, and then plateauing and then declining again. So these types of changes we can see are based off of maybe things that are within the data, or with regards to public health policies and stringencies, maybe things that are outside of the data sets as well. And moving on to kind of this next feature of seasonality, seasonality based off of the first visual that we saw, it shows this kind of harmonic cyclical oscillating pattern. And so what we define it as is a consistent systematic pattern, commonly modeled with harmonic functions. So you can see this kind of sine term and the cosine term, and we'll get into, for those who are more in the math side of things, we'll get into all the equations on the next slide. But most importantly, when we think about seasonal features, we have 5 different attributes that we really like to dive into from a kind of disease surveillance perspective, all of which have slightly different utilities when we're starting to think about planning for preparedness plans and thinking about how we respond to disease outbreaks from a policy standpoint. So one of the most, or I guess the 2 most featured in the literature, especially nutrition epidemiology literature, is peak timing and amplitude, which refer to the time in which the epidemic curve reaches its maximum, and the amplitude being the difference between the minimum and maximum, or what we call the nadir, and the peak of the curve. And so the timing is very useful, especially for things like influenza or salmonella that may have stable seasonal patterns, to be able to understand when the volume of cases or the volume of incidents increases and is planning on increasing. It's extremely important from a resource allocation to be able to know roughly when we need to have resource mobilized by, and amplitude being how much resources or how many resources need to be mobilized in what quantities. We can also think about the timing of the peak for, say, vaccination scheduling. If we know when the peak is going to be, how early do we have to begin these vaccination scheduling and campaigning in order to try to reduce the amplitude, reduce the overall intensity that we see of an outbreak. Duration is kind of common to what you might hear with like a flu season, or maybe what may come with a COVID season in the future, who knows? And that's the duration from when we see kind of this onset point to a return to what we might call endemic levels. And that's a little bit harder to estimate, really, depending on what you define as the threshold of onset. We've worked on some of our new smoothing techniques that try to define these periods using more of a data-driven approach, but oftentimes historically, these have just been levels that are defined over years and years of data, where we try to estimate a specific threshold at, say, the 25% level or 50% level, whatever it might be, to be able to define when we are at an endemic level below this point or an epidemic level above that point. And then finally, the last 2 components are the rate of acceleration and the rate of deceleration, which is now talking about how quickly are we moving from a nadir to a peak, and similarly from a peak back down to a nadir. With the combination of these 5 properties, we can really define pretty much any curve that comes. And that allows us, from an analytical side of things, to be able to estimate each of these features in turn and really determine kind of what our next steps are in terms of modeling and forecasting of disease outbreaks. For you math nerds out there like me, we have lots of equations, but the reason partly why we use harmonic regressions so commonly is because of the stable features that harmonic regressions have. So the combination of sine and cosine, if we remember back to our early days in calculus, we can think about the unit circle, thinking about this combination of sine and cosine from a circular standpoint. And these are wonderfully developed by actually Dr. Tanya Alarcón-Falconi. And what's beautiful about these types of curves and their patterns is that if we think about time as a construct, it's not necessarily just linear. It's not this notion of going from point A to point B, but instead we can think about it from a season standpoint, season being perhaps a peak and a nadir within each year. We can think that a year actually is a circle. And we can think that that circle begins at the start of the year, say with the 1st of January, we go all the way around back to the 31st of December, and we can continue to go through this process every year. So by taking the harmonic terms from that model, we can then actually identify, based off of the sine and cosine beta coefficients, where on the circle we reach our peak, and based off of that, return what was a circular pattern of time to now what is a linear pattern of time, where we define the beginning and end of a year and identify when the peaks are within that year. And when we think about time series, that's partly why it's so useful to have longer stretches of time where we can really evaluate not just the seasonal pattern that may come from one curve, but we can also start to break it down into different years. And we can begin to assess, is there a stable seasonal pattern that occurs on a year-over-year feature? Do we see a similar peak timing each year? Or do environmental parameters or other parameters and risk factors drive the peak timing to shift such that we may be able to pick up shifts in the peak time of when it may occur? And we can understand what are the driving forces that maybe make an infection peak earlier in a year versus later in a year. Perhaps with climate change, warmer temperatures drive maybe an earlier peak timing, or perhaps we do a great job with a vaccination rollout and perhaps it delays the peak of an infection. And so this is one of the works that we had done on salmonella in the United States. And we can see that salmonella is a wonderful example of something that has a very, very stable seasonal pattern. We can see that over the course of the year, the peak timing seems to arrive right around the same time in July and August. Yet we can also see that the amplitude of the curves vary each year, which may be driven by a variety of different factors that were somewhat outside the scope of what we were working on. And we can also think then, if we're taking each year by its own individual pattern, we can start to think about shifts and drifts by plotting them in a slightly different way. So thinking about if we were to plot them now in a forest plot by each year, we can see what is this relationship between perhaps a disease that peaks earlier in the year, maybe having a lower amplitude, versus peaking later in a year and having a greater amplitude. And similarly, looking into temporal patterns and their relationship to other things, say with latitude, or things with, say, completeness of the data, or things with, say, the number of the wealth or the income of a specific country. So in this case on the right, we actually have influenza, and we can see that most of these countries here are actually from European region, and have very, very early peak timing in the year at a very high latitude. And typically based off of our heat of each of the dots, we can see actually have a high completeness or a lot of data that is usable to be able to analyze these outcomes. As compared to closer to the equator, we actually see that the peak timing varies dramatically depending on which, I guess, ultimately where you are as you approach the equator. But you can also see that the completeness of data also decreases for countries that are by the equator. And you can see that oftentimes they have lower rates overall that are being reported, which may be driven by completeness or perhaps driven by their location. So overall, in time series, we can get very, very complex in these things, but hopefully between these plots and what we can see from, the importance of having data from long periods of time to assess these different types of patterns, we can also note that it's really important to have proper data quality. So very, very quickly, because I know I'm running short on time, just to discuss notions of data quality. Why does data quality matter? Why do data matter when we do time series modeling? And part of that is from a data quality in the sense of accuracy and precision of the actual data that goes into our models, but also part of its data credibility, which is a little bit more of the focus of our works, that focus on how do you inspire belief or trustworthiness of the data. Because as we saw in our previous figure, some of these patterns may simply be driven by how much data is actually usable and complete that we can take and put into a model. And that matters just as much as perhaps what the data is telling us. So the kind of classical approach to thinking about data quality, we think about a bullseye. We can think about more accurate being closer to this gold standard of the center of the bullseye versus more precise, which is also perhaps all the points are in one place. They may not be accurate in the sense that they're all by the bullseye, but being as close as they are to each other allows them to be very, very precise in the sense that there's limited variability of observations, and then accuracy allows us to reflect how much are they in terms of the truth. But when it comes to assessing that for time series data, it can be quite challenging using public health surveillance systems to really know how precise and how accurate data are. Oftentimes they're collected by someone besides you as a data modeler. They're oftentimes reported without very clear or specific metadata to describe what the techniques were that were used. And when it comes to having a gold standard, it's very hard to know what exactly a gold standard would be in that sense. We may think that there's certain organizations that have a higher standard of data collection than others, but how do you exactly translate that into your modeling approach? How do you consider that when you start trying to do predictions of what diseases should be? It becomes quite challenging. And so oftentimes we're forced to just take data at face value that it is precise, that it is accurate, and then try to adjust our models to look more at things that we can control, or things that we can begin to understand and assess from a quantitative standpoint, which really gets into data credibility. And so some of the terms that, again, I take no credit for this. This is predominantly coined by Elena a long time ago, which was the A's, the V's, and the C's, which I think at one point was the A's, the C's, and the E's of data credibility, and the variety of different metrics that we have to assess data credibility. But what we can think about is, from kind of standard epi approaches, we think about things like sensitivity and specificity, false positives, false negatives, sample size, power. So how does that translate into now an analysis that's being conducted over time, where time is the primary unit of focus and of interest, rather than, say, the relationship between one outcome and another outcome in a cross-sectional or cohort or longitudinal setting. So when we think about these, we can think about things like availability. Is the outcome available, the outcome of interest that we want? And if it's not available, or if it is available, is the case definition that's being used in one location the same as the case definition in another location? Similarly, we can think about comparability. Do we have different locations where we can begin to compare, or different diseases? Like in the case of Salmonella, how does Salmonella's peak timing compare against other infections? Is it similar? If it is similar, how do then we modify our recommendations in order to capture a larger branch of infections that may have similar pathogenesis, but ultimately have similar or different peak timings? We can think about volume. How much data do we have? And more importantly, completeness and velocity. So velocity, at what frequency are they being collected? And completeness, how much of them are available? Just because we have a full-time period for which data is collected and a relatively frequent velocity by which that data is being collected, that doesn't necessarily mean that we have very complete data. And the picture that we might be able to make with more complete data will look a lot different than with less complete data. And ultimately, accessibility is a huge issue when we start thinking about surveillance systems and the availability of data for public reuse. And so, again, these patterns all come in when you start thinking about downloading data and pulling data from different areas and in different places. And when we start thinking about, from a modeling standpoint, what this means, you can see just simply 5 seasonal curves is just a rough estimate. We can say, well, what happens if we have a peak timing, and one is in June, 2 in July, 2 in August? Well, what happens if our data is complete only up to a certain point? Now we would estimate that actually the peak timing is closer to August than it is to June or July. Or perhaps we lose the end of our time series. Now we're thinking maybe it's only in July or earlier in mid-June. And then we can think about, well, what happens if we have time that's missing towards the peak? Now we actually have no idea whether the peak does occur within these gray bars or not. And by that means, we have no idea whether these two curves may actually be connected, or whether there is truly a return back to a nadir standpoint. Similarly, when it comes to amplitude, we may have a certain understanding of how many cases are occurring for an epidemic curve. And at the same time, we may have no reporting as we get towards the peak, which is actually somewhat common, and one of the biggest challenges we were facing with COVID, of not knowing not only when the peak was going to occur, but whether we would continue to go up or go down afterwards. And finally, from that seasonal standpoint, there's not just completeness for the whole time series, but we can think about how much completeness do we have on an annual standpoint. And so this is one of the pieces of work we did on influenza, thinking about, for each of the different countries within Pan America, how frequently were they reporting data and how consistently were they reporting usable data that we could take on a year-by-year basis. And we saw that some countries, specifically countries that had higher public health expenditure, tend to have more completeness and a higher percentage of completeness each year as compared to other countries, specifically those within kind of the Caribbean and Central American region. But it also differed by outcomes, where for some outcomes, we may have quite a bit more data or surveillance that was more consistent throughout an entire time period, versus other things like, say, H1N1, which is what we see here, the pandemic that kind of kicked off in 2008, 2009, where we can see that there's actually no reporting beforehand. So we have to be conscious when we do evaluate data quality that we're considering these factors of, even if a surveillance system has no data, why? I think that's the most important question. Why is that data missing? Is it because of something like H1N1 where it didn't even start until 2008? Or is it something that may be more addressed by an expenditure standpoint? So with that, we kind of key messages, big takeaways, that time series analyses are very useful for evaluating time reference data, that these patterns can have very kind of consistent linear trends or nonlinear trends. They may also have irregular patterns that need close inspection, that aren't just simply assuming that the data is truly precise or accurate, but may be driven by things like policies or changes in surveillance systems outside of what we know to be true with the data. We can think about seasonality, which is these consistent symmetric patterns that happen, harmonic functions being quite useful based off of their properties to assess and estimate peak timing and amplitude. And ultimately the role that data quality and specifically data completeness plays in being able to understand the features of these curves from a modeling standpoint, and really forcing and hoping that all modelers will consider the curation process and the entire data lifecycle of how the data comes in, how it's processed, how it's managed, and more importantly, its usability and how that might affect your modeling approaches. So with that, thank you. I think we'll turn it over to questions. And most importantly, I want to just give a huge acknowledgement out. This is a massive team. The works presented here by no means are my own. They're definitely a huge collaborative effort by the Informe group. You can see Maia's name on there. You can see Emily and Elena and many others who have been extremely supportive of this process, and also wonderful funding coming from USDA NIFA, from ODNI, IARPA, NSF, Tufts University, and the Stop Spillover program at USAID. So just thank you to everyone, and I'll turn it over to you, Maia.
Great, thanks, Ryan. So now we're going to move into the Q&A part of this. So if you have a question, feel free to throw it into the chat box, and I can ask it to our presenters, or if you want to raise your hand, I can ask you to unmute. But we already have one really good question in the chat from Kelly, asking, when there are big gaps in the data for certain timeframes, what are the best practices for eliminating what might be happening with those gaps? And is it possible to compare a lot of different possible scenarios, or are there better strategies?
Sure. Yeah, that's a great question, Kelly. I think you start having to really think about, based off of the spatial and temporal granularity you have, whether the data is usable for the purposes you want. It's more so thinking about, is it the right data source, perhaps, why that data is missing. And in terms of harmonization standpoints, I think harmonization with time series data is very challenging, just simply from the grand scheme that not a lot of data is reported with consideration for things like time. And so when you're trying to merge data from multiple sources, you may have issues with regards to, well, one is monthly and one is daily. So I have to really take the daily that I liked, now aggregate it up to monthly, and then combine it. And is it really the same story that you're trying to ask? When you have big gaps like that, I think the most important thing, which really in nutrition literature we struggle with, is reporting it. We often don't talk about data limitations. We don't talk about how much missing data, how much complete data we have when we're doing these analyses. And I think that's criminal to some extent. I feel like we really do need to focus more on talking about how much data we have. And then that will be used to kind of justify the steps we take of how we then model these types of temporal patterns.
I probably will need to add a little bit more on a sense of when you have a very large gaps. So sometimes those gaps are absolutely valid, they're justifiable. Think about, for example, analyzing data for famine in specific area. You will not expect that famine will be consistently going there for many years. It will be like one segment, then it will be quiet time, and it's another starts. So it would be a gap in data in many different ways. So in this situation, necessary to think also what would you be able to ask, how you will frame the questions. Maybe it's not a traditional way of dealing with data. It should be way more adjusted, not about the data availability, but biological processes, sociological process you want to address. And this is again become really very important, how the questions were typically asked. There are not, time series is just only, one of the instrument, one of the tools, and we simplify that tool to make it again palatable for the area of interest. We are in many domains who are using, for specialists who are using time series as a really very valuable tool of analysis on a daily routine basis. These challenges which we are experiencing are probably foreign, and they're not really very often experienced with this type of conditions. We also need to think about what it means large gap, on what extent, from what perspective, and ability to also to assess, ability to collect data frequently, regularly. Sometimes it's extremely expensive too. Sometimes the process is not changing, not moving at all. And thinking about how much resources you need to use to keep a continuous surveillance system, these very important aspects all need to be taken into account. But that's a wonderful question, and I believe that everyone probably need to think about more of overall strategy and research questions associated with that.
Thank you, Ryan, Elena, and Kelly for that. So like I mentioned, please feel free to put more questions in the chat box, raise your hand, and I can ask you to unmute to ask it out loud. So we have another question here from Greta. So when it comes to modeling, how do we take into account time dependence in the data?
Thank you, Greta, very much. It was really wonderful to have you here, and thank you for the question. And I would say it is a challenging issue. If we, for example, think about modeling some processes, especially point source exposure, in a traditional sense, in a traditional way, time dependence is not very strong. It's actually a very weak construct. But when we talk about modeling, like COVID, where the transmission rate is extremely high, and the temporal dependency, through the network, through collective exposure, becomes such a daunting process. We need to be extremely careful about what kind of interpretation we can bring together, what those interpretations are really related to the biology itself. But it's also think about what is the practical implications, what kind of questions is actually asking us to do. If we are only looking for, let's say, weekly effects, which are really very stable and very well pronounced in many data sources, including COVID data, this time dependencies is actually what we are searching for. We really need to identify those patterns, be able to quantify this pattern, and really learn to characterize it in a way that it would be not only suitable and palatable for people who are purely working on a time series analysis, but also for public health professionals who will ask us to translate. And that's really one of the key issues in this specific regard. We in different construct, of course, we can incorporate statistical techniques, considering autocorrelations, cross correlations, considering different pattern of those correlations with respect to delay functions and cascading effects. But that's extremely challenging issue, and we perfectly recognize the existing challenges, and watching very carefully what is done in other disciplines, so we can adapt, we can adjust, and we can borrow the knowledge generated in many other settings and apply it to public health conditions.
Thanks, Elena, for that. So could we use repeated cross-sectional data for time series analysis?
Yes, we could, but we need again to think a little bit more about the framework. There is a fantastic work done by statisticians focusing on repeated measurements. There is a whole entire slew of already a generation of scientists who are working on using mixed effect models adapted to longitudinal data. And this type of analysis are extremely powerful, very well understood, very well demonstrated the advantages of using this type of analysis for repeated designs. In fact, very soon, the special issue of International Statistical Review will publish paper by Nan Laird, where she is planning to summarize 20 plus years of experience and advancements in this area and this design. So I would highly recommend to pay attention to these directions, and many courses in Boston University, at Harvard University, teaching these courses very effectively. So I will also suggest students to pay attention to all the resources which are available around us.
Perfect. So we can use time series to look at a number of different granularity levels. So what are some challenges that we face in analyzing time series data at a non-granular, more international level versus really granular national or county levels?
I believe the most important issue here would be understanding what that variability associated with the time frequency will really truly means. So sometimes it's exactly the focus of our interest when we are looking for highly granular data, because we're trying to understand fast changing volatility in data. But sometimes that's not really the interest at all. We are looking for maybe slow processes of changes, and these changes are not really very easy to detect. In any dynamic process, one of the most important decisions is that the faster the process will change, the more frequently we need to have that data available. For the more slow changes, more rarely collected data will probably pay the same type of, contain the same type of information, or I would say uncertainty as well. So it's necessary to wait very carefully what kind of answers we will be able to respond. But if we are looking for a process which have a very heavy and very well pronounced, very substantial seasonal variation, we know for sure that the annual data will mask it. So if that would be a question, that would be really very helpful to know exactly what you're trying to catch.
I think it also depends on the meaning you're trying to get from the data. So you may want to analyze local data on, say, an infection that has similarly local and granular levels of temperature and humidity or other risk factors that may be driving what you think are driving the disease outcome. But if you were to take something on a national or international level, yes, you can very easily find data on temperature and precipitation, but what does it mean? What is its value? If I were to take the average temperature for the US, the average temperature for California, that just because you can find that data and harmonize that data doesn't mean there's a whole lot of meaning in that data when you then try to run your analysis. That doesn't mean you should exclude it. But I think, like Elena said, we have to think about what's the frequency and completeness of the data, but also thinking about what is the value. Kind of those 6 data, I don't know if you happen to see Nathaniel Newland's presentation earlier, but the 6 principles of big data, I think value is one of those, and kind of what is the value that comes from the data and how we use it to then answer which types of questions is really something to think about when we start thinking about time series analysis.
Thank you both for that. So would you be willing to talk about ways to communicate results of time series, especially for non-predictive analyses?
And I fully agree with Ash. That's really very challenging, because if we will think about even we just only parse the data on trend, seasonal pattern, and let's say weekly cycle, for data which are available at this level, like we immediately need to describe it in 3 different components. So the interpretation become clumsy, become really very difficult. So we might spend some certain amount of time on modeling, but probably even longer time to understand how to present that information. And probably different audiences would be interested in different aspects. We underutilizing in public health arena the use of presenting the results of a regression model as a predicted value, not for the future, not for the forecast, but let's think about what is a potential scenario this type of a data can describe. And maybe that's a way how we can start to think about better communication. But you're absolutely right. It's not as simple. In epidemiology, I think one of the biggest jump jump in using the statistical models and especially regression models, it's just because of assume people grasp idea how to interpret that results and present it to a much broader audience. It start to take roots. With time series analysis, it's more difficult. I would say the language we are using in this talk are quite difficult and different from what you will hear in the classical talk in time series analysis. And it's done for a reason. For 10 last years, or probably even longer, I have trouble of finding the way of communicating these tools into the public health arena, just because of, again, challenges and difficulties of understanding. Many of you probably will go to conference and as soon people hear the words time series, the only idea which come in mind, it's basically talk about, the line across couple of, points on of annual data. And that's where the time series analysis stops without really sufficient details. So I hear your concern and I share that concern. I think that we all need to work together to find these very important clues and to test with our audiences what works for that, for what works for our audience, what messages become really very prominent and clear and understandable, and probably come up with a variety of different solutions and test those solutions and see which will stick.
So we have time for a couple more questions. Kelly, I'm going to ask you to unmute yourself if you're able to now.
Sure, yes, thank you. I'm going to go back to the question of gaps. I was thinking about your point, Ryan, about sometimes there are environmental factors or factors outside of the data itself that create these big shifts. I think when you have really granular data, you can almost say, yeah, this shift is exactly due to this policy implementation or whatever. But when you have much less granular data, so maybe you have data once every decade, there may be lots of things that are happening in between that decade. How do you recommend kind of getting at the degree of variance due to that particular policy change or environmental change during a big gap?
Yeah, that's challenging. And honestly, I think even with the local and granular data, it's not as concrete. Some of the work, actually, Brianna Lauren's on the call. So some of the work we've been doing with her on mobility in COVID, we wanted to say that it was related to COVID policies. In fact, it had nothing to do, or not nothing, but less to do with COVID policies than it was simply holidays, right? People tend to be more mobile in holidays or more mobile in the summertime to go to Barnstable County out by the beach. So some of these things are not maybe driven by what we think and instead driven by completely different factors. But when you do have data that, so much is changing between data points, like I know Ash, who's also here, does a lot of work with smart surveys, which are collected, say, every 5 years, or the DHS types of surveys. It becomes challenging because there's a lot of things that do change. And oftentimes these types of longitudinal cross-sectional studies, there's a lot of different things with regards to just how data is even sampled and trying to kind of understand that. So again, I think it roots partly with communication and making sure that you communicate the limitations of that, and also just how you define then your question, right? If there's so much that can vary and you're using data that changes every 5 years or that's only reported every 5 years, what are you hoping to see? Are you hoping to see then, changes within those 5 years? Because you really can't, because you don't have any data that can support it as easily. You could say, what are the changes between year 1 and year 5 or year 6? And useful when you start looking at changes over each reporting period. But again, that's more so showing you one time point and another time point and nothing in between. And I think that's something where you have to think about, maybe your goal is to look at not changes that happen over the period of 5 to 10 years, but instead things that change over the period of 50 to 100 years. You know what I mean? And starting to think about what are these longitudinal changes that are happening and ways of being able to say, are we moving in the right direction from a policy standpoint? But ultimately, these larger, I think, these larger types of analyses, again, they answer one set of questions, but I don't think it's one of the things that Elena says to me all the time, and it sticks very, very often, is, it's not just about running one model, right? It's about running a selection of models. And I think when it comes to time series, it's not just about analyzing one data set that may have data at a certain frequency, but actually analyzing multiple data sets within the same realm that provide you different flavors of the same story. So maybe one data set's showing you changes over 50 years with a 5-year interval, but then you take just one 5-year interval, you get very granular data and you say, well, what's happening at this local set? And you're able to kind of start to piece together different patterns from both national and very, very long and broad infrequent time series to very, very granular and frequent daily data, and be able to kind of pull together different stories from different data sets in different ways to communicate ultimately what your goal are and your recommendations.
And Kelly, I was also thinking about sometimes we need to maybe switch questions and ask, and why that data is not available. Maybe it's not accessible. Maybe it is not really possible to reach the population. Maybe there are some other very important reasons. And I think that sometimes learning the structural missingness in the data by itself, bringing really very important questions to ask. And it will give also probably trigger a thought process in terms of what can be done in order to collect that data, like where the challenges in general, and how much it will cost. So like all these aspects are really very valuable too.
Thank you both for your answers, and thank you everyone for your great questions and participating in today's session. And thank you to the organizers for this conference as well for setting up such an informative and interesting session. I'm going to end it here since there's another session following this about careers in nutrition epidemiology and data science, the link to which I've posted in the chat. So we hope that you will join us there. Thanks everyone and have a great evening.